Thank you for the introduction. So I'm presenting today my work with my advisor Zala Lenačić. So before going to dissipative systems, I will first recap what we know about thermalization in isolated quantum systems and how statistical ensembles arise when describing thermalization. So the setup is that we have an isolated quantum system in some initial state, and we let it evolve according to its internal dynamics. And then we ask ourselves if we can say something about the state of the system after a long time, if we know the properties of the Hamiltonian. And indeed, we can say something about local observables after a long time, and in fact, their expectation values are equal to averaging them over some statistical ensemble. So for the purpose of our research, I'm interested in two cases. The first one is what we call a generic system. It has only one conserved quantity, the Hamiltonian. In this case, the system acts as a thermal buff on a local subpart of the system, and therefore the expectation values of local observables after a long time are equal to their expectation values in a thermal Gibbs ensemble. So the thermal ensemble is characterized only by one parameter, the inverse temperature. The other systems we are interested in are integrable systems, which have infinitely many local conserved quantities commuting with the Hamiltonian. In this case, the expectation values of local observables after a long time equal to their expectation values in a generalized Gibbs ensemble, which is characterized by infinitely many Lagrange parameters, each corresponding to one local conserved quantity. So due to conservation of local conserved quantities, the Lagrange parameters in the steady state are determined from the initial conditions. So we can write down a set of equations for each local conserved quantity and solve them to find the steady state Lagrange parameters. So another thing people were interested in is what happens if we weakly break integrability by a static perturbation. So here the integrability breaking parameter G is very weak. And what they have found is that even if the G is very small, at long time scales, the steady state we obtain is not a GG, but a thermal state. But at some transient times, a pre-thermal state equal to the GGE will be obtained. On the other hand, it has been proposed that if the if the perturbations are not static, but rather dynamic, for example, we have driving end openness, then the steady states obtained can be of a non-trivial GGE form, approximately. So this brings me to the outline of the talk. First of all, I will describe the mathematical ground for describing such systems, and I will put them in the context of Limbladian time evolution. Then I will move on to a simple system of free fermions, which are weakly open with the Limbladian evolution, and derive a scattering equation for single particle occupations. And in the end, connect all this story to a recent setup realized by Google Quantum, where they simulated dissipation on a digital quantum computer. Okay, so one way of simulating open system dynamics is via the Limblad time evolution, where we have a dominant unitary evolution. In our case, we take this Hamiltonian to be integrable. And then we have a dissipative part, which is of Limblad form. And in our case, we take the dissipative part to be very weak. So this epsilon is very small. A general property of such systems is that there exists a unique steady state after resolving for all symmetries, and the steady state is a formal solution to the Lindblad acting on the density matrix having to be 0. Let me go back to the picture we saw before. In Lindblad evolution, what we see is that every initial state has a unique steady state, as I've said. And in our case, where the epsilon is very small, I will show you that the time evolution after some long times happens in the GGE manifold, and therefore can be described by a time-dependent GGE, and the steady state by some steady state GGE. So yeah, let us write down some perturbation theory, since we have a weak, some small parameter. So we write down the steady state in terms of this parameter epsilon. The 0th order we denote by rho 0, and all the other orders are denoted by delta rho. Then we want to solve the stationarity equation term by term. And in the 0th order, what we see is that we should satisfy this equation. So the Hamiltonian has to commute with the 0th order of the steady state. This means that we can take for the rho 0 a diagonal ansatz. So it's a linear combination of projection operators onto the eigenstates of the integrable Hamiltonian. But the 0th order doesn't fix the coefficients a's here, and we have to go to first order of solving the stationarity condition to find the coefficients. And the steady state condition is given by this equation. So the diagonal matrix elements of the dissipator acting on rho 0 have to be 0. On the other hand, inspired by the situation in isolated quantum systems, if we go to the thermodynamic limit, it has been proposed that rho 0 should equal to the GG state. So in this case, the local conserved quantities are the conserved quantities of the integrable system. And then the stationarity conditions are given by this equation. It's an equation that states that the flows of conserved quantities in the steady state have to be 0. So solving a set of these equations, we obtain the steady state Lagrange parameters. Note here that the Lagrange parameters are here set by the dissipator and not the initial conditions, since all the initial states thermalize, equilibrate to the same steady state, which is unlike in the isolated system case. Okay, so what has also been done is by Zala and her collaborators in Köln, is that they propose the dynamical equations of motion for the Lagrange parameters inside the GG manifold before equilibrating towards the steady state. So how we see this, the dynamics of the state, is that we have some initial state which is not necessarily in the GG manifold, but then it prethermalizes according to its unitary Hamiltonian evolution to some GG state, and then the dissipations kick in and drive the system inside the GG manifold slowly towards the steady state. So the equations of motions for the Lagrange parameters are given these equations. The second factor we can recognize as the flows of conserved quantities at some point in the GG manifold, and this is a connected correlator between conserved quantities. Then we can represent the flows of Lagrange parameters as a gradient field on the GG manifold, where the fixed point is the steady state. So in the fixed point, the flows of Lagrange parameters as well as conserved quantities are 0. Okay, so they also provide us with an example where they first show on small system sizes that the diagonal ensemble ansatz a good description for the exact solution. So they look at different couplings epsilon, and they show that the diagonal ensemble solution lies on top of the exact solution very well at late times, while there is some discrepancies in the transient dynamics. And this they interpret as finite size. The problem is that we are in finite sizes. Okay, and what this picture tells us is that the diagonal ensemble ansatz is a good expansion point for the description of the exact solution, even at not only for the steady state, but for late times as well. Okay, so the second thing they compare is on larger sizes, the diagonal ansatz and the truncated GGE ansatz. In this case, they take only 4 most local conserved quantities, and what we see is that already taking only these 4 ones, the solutions lie on top of each other quite well. There are again discrepancies, which could be finite size effects and the fact that they didn't take all the local conserved quantities into consideration. Okay, so now on to our recent results. What we wanted to do is to obtain some thermodynamic results, which can be obtained for free fermionic systems. So for the Hamiltonian, we take a free fermionic system. We choose the transverse field Ising model, which can be mapped to free fermions using the Jordan-Wigner transformation, Fourier transformation, and Bogoliubov rotation. And from this form, we can clearly see that the quasi-momentum occupations are the conserved quantities of the system. Then the natural thing is to construct the GGE from using these quasi-momentum occupations, and the Lagrange parameters here are denoted with as chemical potentials. This is a bit different from what I was explaining before, because now the conserved quantities are not local, but one should know that quasi-momentum occupations are just a linear combination of local conserved quantities. So these 2 descriptions should be equivalent. Okay, so we chose to apply a Limrad operator of this form to our free fermions. This kind of Limrad operator gave us a non-trivial steady state, while it is also has a compact form in the free fermion picture. It also causes scattering between the Bogoliubov quasi-particles, so it should give us some interesting dynamics. So here we write down compactly the equations of motions for the momentum occupations. We see that we need to calculate some expectation values of such expressions inside the Gaussian GGE, so doing weak contractions. And after we plug in the exact form for the Limrad operators, we obtain a very compact equation for describing the changes in the single particle quasi-momentum occupations. So the point here is that we have a weakly interacting system, and in the zeroth order, we can write down the equations of motions in terms of some kind of scattering equation between the single particle modes. The first 2 terms here we can interpret it as 2-particle scattering. The third one is pair creation, and the fourth one is pair annihilation. So the point is here that we took bilinear Limrad operators, and therefore we get 2-body processes. If we took something more complicated, we could get also more body processes. So now we can just choose some, maybe I should comment that these functions here are given by the parameters of the Limrad operator and the system, and also by the exact form of the Limrad operator. Yeah, so now we can choose some parameters and an initial state and simply numerically integrate the momentum distribution time to obtain time evolution. We choose for the initial time this black distribution, which is a thermal distribution at some positive temperature. And in the end, we obtain the steady state distribution given by a red curve here, which is quite obviously non-thermal. And okay, also on the right-hand side, I show expectation values of local conserved quantities in the spin basis for the steady state. We see that they fall down quite quickly, and so from this we can conclude that also the local GG in terms of spin basis would be a good ansatz for the steady state. Okay, so we can now use all of our knowledge we obtained from considering free fermions in the continuous case to describe a setup which was recently realized by Google Quantum, where they simulated dissipative dynamics on system qubits using ancilla qubits and coupling the ancilla qubits with system qubits after every block of time evolution for them separately. So first, time evolves with some unitaries separately. The system evolves with the Floquet protorized transverse field teasing. The ancillas time evolve with a very simple unitaries, and then they couple them with a swap operator. And after every t steps of such time evolution, they reset the ancillas to all down state. So by doing this, they simulated dissipation, and they showed that they obtained some cooling protocol. So they go very close to the ground state of the system, so of the trotterized transverse field Ising. So our idea here was that since they used very weak coupling of ancillas to system, we could use our description to discuss this kind of system. We changed it a little bit. So we changed the couplings between ancilla and system qubits to be free body operators. We do that because we want to obtain exact results in weak contractions for the single particle momentum occupations, which couldn't be done with the I-swap operator, but can be done by using our kind of operators. Okay, so in order to proceed, we first needed to derive a Lindblad type of equation for this kind of setup. So we start by calculating the change of the system's density matrix over one reset cycle. And we do a standard derivation of the Lindblad equation in the interaction picture. There are a few differences with the standard derivation. The most obvious one is that we are now in trotterized dynamics, but this derivation can work since we have weak coupling between system and ancilla qubits. Then also after every reset cycle, the ancilla qubits are exactly in a product state of all spins down, which help us with the derivation. And then finally, we also assume that the coupling between system and ancilla is weak, and therefore we have a diagonal ansatz for the system's density matrix. Finally, we obtain this equation of motion for the system's density matrix over one reset cycle. We see that it's of Lindblad form, where the Lindblad operators here are the Q operators, so they are the part of the coupling operators which act on the system qubits. And we also have here a function which we call ancilla correlation function. It contains all the information about ancilla parameters, its dynamics, and also the coupling, exact coupling between the system and the ancilla. Yeah, so we have now dynamical equations which can describe the system's density matrix. And finally, to do this all, the whole thing in free fermion picture, we also need to map the trotterized transverse field Ising to free fermions. This can be done using similar procedures as in the continuous case, but we obtain a little bit different results. But mostly it's we're doing the same thing as before. We choose this kind of Lindblad jump operators, and finally we obtain a similar scattering equation as we've seen before. Now it's dressed by this ancilla correlation function as well. So yeah, it's okay. The dynamics here we see that can be very rich. So we can choose the ancilla parameters freely. We can choose the system parameters freely, and for example, we chose for some parameters that we've chosen, we've done numerical integration from infinite temperature state. And we've obtained again some non-trivial, non-thermal steady state. Okay, but if we want to see in the quantum computer if we've obtained a GGE or some thermal state, we cannot just measure momentum occupations, but rather some local operators. And in fact, what they can measure is this kind of operators. So they are sigma y's on the edges and sigma z's in the middle. These operators are a part of local conserved quantities of the transverse field Ising. And we can increase the string of sigma z's in the middle and calculate the expectation values with increasing the string in the middle. So here we compare what we get for the ground state of the Floquet transverse field Ising and what we obtain for the steady state. And what this picture tells us is that we have prolonged correlations for this observable in the steady state, which means that the local conserved quantities of this, which contain this observable, have more importance than in the ground state. And this we interpret as the fact is that we have a GGE rather than some thermal state. We can also control the correlation length by increasing the time between two resets of ancilla. So if we increase the time between two resets, we can increase the correlation length for this observable. Okay, so the moral of this quantum computer story is that if we have weakly interacting ancilla and system qubits, the system is prone to relax to a highly non-thermal GGE state. Then in our case, we have free fermionic system weakly coupled to some to ancillas. We can write down equations of motions for single particle occupations with some kind of scattering equation. And then if we want to obtain, for example, ground state, or we want to simulate cooling, we should think how to tweak the parameters such that this the annihilation processes are the most important ones. So in fact, this is what they showed in a paper following the realization, that they did shape the coupling between the system and ancilla qubits in such a way that they obtained dominant one body losses. So this is why the cooling procedure worked. Okay, so this brings me to the conclusion. I've presented today to you how generalized Gibbs ensembles arise in weakly open quantum systems. I've shown that the dynamics at late times is given by a time-dependent GGE. And then I use this kind of description for weakly interacting free fermions. And I've obtained the scattering equation for given particle occupations, and I've shown that the transition rates are given by the buff. Then finally, I showed how we applied this to a digital quantum computer protocol where the system is coupled to ancilla qubits, which are reset after every now and then, and this simulates dissipation. That's it, and thank you for your attention.
Quick question. So in terms of your understanding, can you create now some trivial states, right? Or what if I want to create some interesting correlations now in the system? How much freedom do I have within your framework, right? So if I maybe adjust only a few parameters in the coupling, what is interesting can be made?
Yeah. Okay. So, for example, these correlations, I could only obtain some exponential decays. I couldn't obtain polynomial decays for critical parameters. So this, for example, I couldn't get, but otherwise, by tweaking these parameters, you can obtain quite different kinds of behavior. So very different distributions, and yeah, so I think you have quite a lot of freedom just tuning these parameters. But if you want like more processes, different processes, then you should change the whole Lindblad operator. So this is a bigger deal.
Okay, so this has been done in the regime of a weak coupling to the environment, no? So assuming you have a slightly weak coupled environment. So what do you think would be the next correction? Non-Gaussianity, or actually still the Gaussian terms which you neglected in your?
It's both, right? Yeah. So it's both, but it's scaling with epsilon. So you have corrections inside the GG manifold, I mean, perpendicular to the GG manifold, so in the diagonal ensemble and also off diagonal. So they are of the same order. So it's hard to just say from generic case.
So in the Google experiment, the coupling was strong, so they didn't find the GG.
Yeah. Okay, they didn't try to fit a time-dependent GG over it, but they did in this paper. In this paper, they did use weak coupling to describe the time evolution of this single particle occupation. So they explained, basically in this follow-up paper, they explained it with weak dissipation.
So then it means that they should have found the DG.
Yeah, no, because they tuned the parameters such that the one body losses were dominant, so they go very close to the ground state. So they are pulling down the system to ground state. So
you don't have this.
No. We just we take a generic Lindbladian to just show that you can obtain non-thermal states, because we also have a different Lindbladian. And they had one body Lindbladian. So they had one body Lindbladian, because you can realize this in quantum computer because it's two-body gate. And we did more body because this doesn't contain strings in the free fermion picture, and then it's exactly you can do weak contractions exactly. So what they did is they expanded the strings to show that and to some order, and then they showed that these one body processes were dominant. But yeah, okay, our point is that you can do more involved scattering equations, and then you should really tune the parameters to have these losses most pronounced.
Question from in these previous works, I thought when these local charges were used, you need only a few of them. Here you need all of them. Is there a way of getting rid of R?
Yeah, you could.
Tied to the integrability of the.
Yeah, you could do this, but okay, for free fermions, you can also do everything. I mean, you can just take all the momentum occupations, but you could also, I don't know, take some actual local observables, conserved quantities of the Ising model, or yeah, some Fourier transforms of the quasi-momentum occupations and truncate them. You can do this, and okay, here I don't show this, but the point here was that basically you could do it because the expectation values of local conserved quantities are falling down quick, so you could truncate and just work with some of the local conserved quantities.
Question over there.
Thanks for the talk. Mine is more a technical question, maybe. So, because you did your calculation, if I'm not wrong, with the trajectory Dyson model, which is a Gaussian model, etc. How much? Question is the following: how much your calculation rely on the fact that you're using the trajectory Dyson model, and how can be generalized to a general Gaussian model?
It only relies on the transformations with the Limbladian. So we took the transverse Ising model because it's a nice spin, discrete spin model, realizable on quantum computers, also on spin chains. And then you have also Limbladians can have some physical meaning. But basically all we needed to do is write down the Limbladian in the free fermion picture. But if you would just take some free fermion Limbladians, you are good to go. You just do weak contractions.
Yes,
Question.
I was wondering, in your protocol, you consider the Limbladian as was quadratic in the fermions, right? Do you think that the picture is more or less unchanged if you consider Limbladian that are, let's say, linear in the fermions, that you can really solve it by, I don't know, quadratic method, Gaussian methods?
I think you will get only one body processes using this, let's say GG ansatz, you would get one body processes only. Yeah, so they should be the same, then they should equal to the exact solution in this case.
I see.
But nobody tested that, right? Nobody published the calculation of that. Nobody's tested. I don't think so.
Yeah, no. I guess
It's super benchmark.
Thank you for the talk, for the discussion.